Hello, all you cool cats and kittens out there. Been waiting for the right day to use that line from the Tiger King. Thought today might be the day. So, this is going to be the last live stream of the week. We'll talk about why in a few minutes. I mentioned it yesterday. But we'll give everybody a couple minutes to jump in. Question of the day is, what is your favorite video game of all time? Game of all time. Not just like your current favorite, but I mean like of all time. The one video game that is the most memorable game for you, the one that like you were the most excited playing, the one that you could probably be on a desert island with for the rest of your life and just play that game. So what is that favorite video game of all time? So about 103 we'll get rolling here, and I will share with you my favorite video game of all time. And while we're waiting, I just want to remind everybody that Friday at 1 o'clock, we are doing a live model rocket launch. I have two model rockets that I'm going to be launching, the Red Ryder and the Alpha 3. So I'm going to be putting these together tomorrow, and we're going to be launching these Friday morning, weather permitting. Hopefully the weather cooperates and we get some decent weather Friday afternoon and we can launch those. I'm going to be taking my kids to a nearby park where I believe we are going to be okay to launch those at. We're not using any crazy engines, so they're not going to be going too high. Problem is when you get into larger model rocket engines, they go really high, like 1,000, 2,000, 3,000 feet, and it's really hard to track those visually. So I'm going to keep these relatively low. Also, when you get into to the larger stages, you have issues with them taking forever to come down, and even if there isn't a lot of wind on that day, they'll get caught in the wind and then they'll move down field pretty far, and it's hard to track them. So, I mean, the rockets that I'm going to be launching aren't super expensive, but when you get into those more powerful rockets, they can be pretty expensive, and it's really sad when you lose them. When I was in high school, I was into model rockets, and I built a 2-stage rocket, painted it, it was awesome, and totally lost that thing on like the first launch. It was terrible. So yeah, these are pretty simple kits. They just kind of snap together. All right, about another minute, then I'll get rolling, and we'll talk about video games for a little bit, and then we are going to move into the lab write-up, which I know everybody is working on at home right now. And I want to remind everybody that this is definitely a skill that you'll need later in life when you go into college, or if you're taking chemistry next year, you will be doing lab write-ups. So this is good practice for when you get to doing those in chemistry or in college. All right, 103, so let's get rolling. My favorite video game of all time. Remember, I grew up in a completely different time. Our video games were a lot simpler back then. My favorite video game of all time was, or is, Final Fantasy VI. There are many Final Fantasies. I think they're up to like 15 right now. Final Fantasy VI was actually released as Final Fantasy III in the United States. It was kind of confusing how they did that. A lot of the Final Fantasy titles weren't released in the United States until later. So there were 2 for the regular Nintendo. That's like old school Mario Nintendo. And then the actual 3rd Final Fantasy that was released in the United States was on Super Nintendo. But it was actually the 6th Final Fantasy in the series. So as you can see, here's a screenshot of the game on the right. It is a role-playing game. Graphics are very simple, but I mean, you could easily spend 20 hours playing that game all the way through. It's a very large game. Graphics at the time were amazing. Now, I mean, they look terrible. So that is my favorite video game of all time. I remember getting it for Christmas one year and just playing it like all the time. Like I would race home from school to play it. And I would buy the strategy guides for it. We would talk about it at school. Everybody was playing this, and it was just awesome. So that's my favorite video game of all time. I want to talk about some of my other runner-ups because I know quite a few of you are interested in video games. So let me just talk about a few of my runner-ups. There's quite a few here. These are definitely some games that I invested a significant amount of time in. Final Fantasy VII was on PlayStation. I played that when I was in the Air Force when we had nothing else to do. Half-Life, that was a big first-person shooter. Now, the original Half-Life, not Half-Life 2. That was a big game when I was in high school. Red Alert 3, it's a real-time strategy game. Alpha Centauri is a turn-based strategy game. I played that, oh my god, so much in high school. Star Trek Online, definitely a nerdy choice. Play it every now and then. Master of Orion's an old-school turn-based strategy game. I played that in high school. And then love the Fallout series. I've played 3 all the way through. I've played New Vegas all the way through, and I'm working on 4 right now. I have a lot of time invested in those games. So, and then the other game, which maybe a little embarrassed to admit that I spent a lot of time playing, was World of Warcraft. A lot of time spent playing that game. I actually, when I was at my peak, I was probably putting in 8 hours a night playing that game, and that's kind of when I realized I needed to time out and take a step back. So I played through the first, I want to say 3 or 4 expansions, and then I was done. So there you go. So if there's anybody that's watching this, looks like I have 1 viewer right now. Type in the chat what your favorite game is. All right. So let's talk about tomorrow. Tomorrow we have an exciting opportunity. Tomorrow, Fermilab is going to be giving a live talk on Zoom about the Large Hadron Collider, which is a particle accelerator, the biggest in the world. It's at 1 o'clock, so I will not be live streaming tomorrow because it takes place at the same time, and unfortunately, I can't move my normal live stream time because I have other things going on in the morning with meetings and such. So you do need to pre-register for this, and let me actually put the link in the chat here. Oh shoot, where is it? Bear with me. Shoot, I just had it up. I swear, I just sent this out to everybody, and I, for some reason, can't find the link. Physics. How did I send this out? Oh, here it is. Okay. So the sign-up link is right here. Let me paste this in the chat. Okay, so if you're interested, you do need to register in advance. So if you click on that link, it's a Google Doc, or I'm sorry, not a Google Doc, a Google form. You fill that out, and I'm assuming that they're going to be sending out the Zoom information the morning of. So tomorrow morning, hopefully, we'll all get the link to register. I'm going to be jumping in as well, so you'll probably see me on Zoom tomorrow. I'm super excited to sit on in it. So if you don't know what the Large Hadron Collider is, this is Fermilab. This is a view of their old particle accelerator. So a particle accelerator basically takes these tiny little particles and accelerates them really fast and then smashes them together, and we're able to do some really cool physics. So the particle accelerator that they had was 3.9 miles in circumference. Back in the day, it was a really big deal, but it was, I believe it's been shut down since 2010. They lost a bunch of funding, and then the new Large Hadron Collider came online, so there wasn't really a need for it. So 3.9 miles in circumference all the way around. Now the new one that's been built and has been in operation is much bigger. It's in, I believe it's in Europe. I can't remember where it is, but it has a 17-mile circumference, and it's massive. So if you look here, I apologize, I know there's a lot going on here, but down in the lower right-hand corner is a picture of one of these tunnels. So imagine 17 miles of these tunnels, and they're accelerating particles really, really, really fast inside of this thing and then smashing them together. So if you remember, well, it's been a while now, but they found the Higgs boson particle, which is called the God particle, quite a few years ago, and it was a really big breakthrough because of this particle collider. So Fermilab is going to be talking a little bit about that. I imagine they're going to be talking about some of the new experiments they're going to be running with this. So it should be pretty exciting. Now, if you do jump in and watch the Zoom, all I need you to do is just shoot me an email afterwards with something cool that you learned from it, one big takeaway, and then I will toss some extra credit in for you in the formative column. All right. So, moving right along here, let's get into some physics. So, for the rest of the week, you are just working on the lab report. Okay, yesterday you should have written the claim and reasoning. Today you should have started the background on the lab report. So, what I'd like to do for the remaining time that we have for physics is to kind of talk about the lab report and then to kind of help get you started on the background information. All right? So, in your OneNote, you should find the shell of the lab report. And I've gone ahead and made titles for everything. So you're just going to replace the title at the top with something cool. You could just call it like Electromagnetism Lab Report or something more exciting. Maybe you can come up with something better. Put your name down here. And then I asked you to just work on the background section today. If you're feeling motivated and you want to do the whole thing, you go for it. If for some reason you're having issues with OneNote where it's not popping up, it's not syncing right, you can just do it in Word or in Google Docs and then just email me the file or a link to the shared file if you're using Google Docs, and I'll be able to grade it that way. Okay? So for the background, there were 4 questions that you need to answer in the background here. All right? Number 1 was what is voltage? Number 2, what is a loop? And that's in terms of electromagnet. Number 3 was how does an electromagnet work? And then number 4 is what is an electric field? Okay, so you can answer these in any order that you want, but those are the 4 things that I was looking for in your background. So I also, if you looked at today's post, pull it up here. Looks like it's going to rain today. No bueno. Today's actually my daughter's birthday. So we have some exciting plans tonight. We ordered her an ice cream cake from Oberweis. And unfortunately, I can't eat it because it's got gluten in it, and I'm allergic to gluten, and that's like the worst thing to be allergic to. All right, so in the post for today, down at the bottom, I gave you some links. Right. Now, yesterday I kind of mentioned that there is actually, if you didn't know this, there is a simple Wikipedia and then there is a regular Wikipedia. Right. Now, I know a lot of English teachers are saying like Wikipedia is this really bad thing, don't use it. But honestly, Wikipedia has gotten to be a very reliable source, especially for scientific articles. They have bots that comb through these articles to help weed out changes that are not correct, just the average person just going in and typing whatever they want. They've kind of put some protections in place, so that doesn't really happen that much anymore. But anyway, if you click on one of these links, this is a simple Wikipedia article on voltage. Okay, so actually you can even see here in the upper left-hand corner, the logo is actually different. All right, but a lot of the information gets pulled from the same source. So for voltage, when we talked about this in class, voltage is that pushing pressure that moves electrons through a circuit. Okay, it even says it right here. It says it is the push that causes charges to move in a wire or in other electrical conductors. Okay, so there you go. There's your voltage. Right? I told you to think about it like pressure in plumbing. Okay, water doesn't really move if it doesn't have anything pushing it. Okay. So that's voltage. The second thing you were supposed to explore, and you don't have to do these in any particular order, it's what is a loop and then how does an electromagnet work. Okay, so if we're going back here, we've got what is an electromagnet. Let's do what is an electromagnet. Okay, so in the electromagnet Wikipedia article, you will see that they talk about how it's inducing a magnetic field. So like talking about loops, talking about the magnetic field, and then talking about how an electromagnet works, you might want to kind of put those in the same thing because they do kind of relate. Right? So a loop is any kind of a circular thing that you have going on with your wire. Okay, so when we talk about electromagnets, it's basically just a complete circle. All right. So when we build our electromagnets, when I built my electromagnet, let me see if I still have it, I ran a wire around a bolt. So when every complete circle around the bolt was considered a loop. Okay, so if I can get that a little closer, I know it might be a little blurry. All right. So an electromagnet is basically a magnet, or it's basically you're giving something a magnetic field. Okay, it doesn't have it unless you apply an electric current. And it even says right here, the coil of wire is called a solenoid. The strength of the magnet is proportional to the current flowing through the circuit. Okay. So we talked about, I believe I talked about ferromagnets, which are basically pieces of metal that have natural magnetic field. Okay, so you've played with magnets before, like the magnets that are on your refrigerator, for example. Those always have a magnetic field. Okay, those are called ferromagnets. But electromagnets, you need to have an electric field flowing through those to be able to have the magnetic field. Okay, so it's inducing a magnetic field. So if I were going to write this up in my lab report for my background information, I would say, let's see, voltage is the pushing of charges through a wire. The wire in an electromagnet is wrapped into loops around a piece of metal. When a current moves through the loops, a magnetic field is induced. A magnetic field functions just like an electric field in that it flows, flows from one pole to the other. All right, so did I hit everything? Oh, okay, so let me just add when the magnetic field is induced in an electromagnet, it functions just like a magnet on your refrigerator. When the current is removed, the electromagnet loses its magnetic field. Done. Okay, so that kind of hits all four things. We talk about voltage, we talk about loops, we talk about how a electromagnet works, and then we also talk about a magnetic field. Okay, you can write. I mean, obviously, I want you to write this in your own words, but if you go through the Wikipedia articles, that is pretty much what you'll find out. You can also use your notes. I didn't ask you to cite anything, but when you get into chemistry, you're going to have to do some citations. But since we went through a lot of this information and it's in your notes, I'm fine with you guys just not citing anything. Okay. Now, since this is the last live stream of the week, I'm going to go through some of the other parts here. A lot of this is going to be copy and paste. So give me just a second here. Let me pull up my other. I'm going to pull up my other piece from the other day. I'm going to do two screens here because honestly it is just copy and paste. Okay, so for the purpose of this lab was to identify kind of your guiding question. So the purpose of this investigation was to explore, and I did the number of loops, I think, explore how the number of loops affects the strength of the electromagnet. Okay. Experimental components are pretty much just the pieces that you have. So let's see, we have an independent variable. NDEP, can't spell. Our independent variable was the number of loops. Anything you're changing in the experiment is your independent variable. So the number of loops, if you did the number of loops, if you did voltage, it would be voltage. The dependent variable was the strength of the magnetic field. Okay, what else did we have? We had our setup was a FET simulation, FET electromagnet. Okay, for our methodology, you can just do it in steps. So I'm going to just copy, Control C, and then Control V right here. All right, so there's my methodology. Figures and visuals will be, you can just copy. I'm fine with you just doing this. You're supposed to kind of sketch out what you did, but check this out. I am just going to go in here. Let me pull up the FET simulation. Why is this being silly? Here we go. Okay. Oh, I know why. It's because it's a Java applet. It's not HTML5. Okay, so all you need to do on this is you can just do a screenshot. So I'm going to screenshot my magnet here, and I'm going to just paste it right here. You could even, if you want to, you could type in electromagnet from FET simulation, just to be thorough. Oh, we could even call it figure 1. Okay, table is going to be your data table, so you could just copy this and paste this. Okay, graphical representation is just your graph, so just grab this, just copy and paste. And then analysis or calculations. Okay, there wasn't anything to calculate, but we did analyze here. So in our reasoning, we kind of do a lot of the same thing in this. There isn't anything to calculate. Let's come back to that one. All right, the claim, we're just going to copy and paste. So copy and paste. And then reasoning, copy and paste. Okay. So in your analysis here, if we were doing any sort of calculations, you would put those in there, obviously. But really the only analysis that we have here is you can talk about the slope here. If you actually had the slope of your graph, you could put it in there. But you know, on here, all I'm going to ask you guys to do is just tell me something about your graph. Okay, so according to my graph, I have a positive slope indicating a direct relationship. You could also add here as the number of loops increases, the strength of the magnetic field increases. Might be a little repetitive because your reasoning kind of does the same thing, but that's it. So as you see, I did that in like what, 10 minutes. I'm asking you guys to just do the background information for today, but if you're feeling motivated and you want to just go ahead and finish the whole thing, you can. I'm going to add here, just to be complete, Mr. Zorn's awesome lab report by Mr. Zorn. Done. Okay, that would definitely be an awesome lab report. Okay, so you can do it in Word, you can do it in OneNote, you can do it in Google Docs. If you do it outside of OneNote, the only thing you're going to have to do is just email me your lab report as an attachment, or if you do it on OneNote, just share the file with me so that I can see it. But these are all the pieces that you need. So if you have questions, if you don't understand a part, just shoot me an email. You can sign up for one-on-one tutoring, and I will go through how to do this with you. But this is it. This is all you have to do for the lab report. So you have the rest of the week to work on this, which is more than enough time for you to do this, honestly. It should only take you one day, but you've got 3. So make sure you have the CER done, and then make sure you also have the lab report done. So the CER you should have finished yesterday. The lab report you need to have done by Friday. Okay? So that's it. And I have one person that's watching me right now, but I haven't heard anything from them. So I'm going to assume that there's no one else with questions here. So for the next couple minutes, I am just going to sit here and look busy while we wait to move on to chemistry at 1:30. let's see. Friday it looks like it's going to be 59 degrees on Friday, and it's saying 20% chance of rain. So hopefully, I don't know if we can do hourly up to Friday. Let's see. Thursday. Okay, so Friday. Oops. Okay, so where did it go? I think it's had Friday at noon. So it's just saying cloudy skies, high 59, winds east to northeast, 5 to 10 miles an hour. So that should be okay to launch if that keeps. It looks like we might get some rain in the evening, which would be okay because we're going to launch around 1 o'clock. So fantastic. Okay, so 1:30, we're going to give anybody that's jumping in for chemistry a couple minutes. But want to just quickly talk about Friday. Friday, we are doing a live model rocket launch at 1 o'clock. And the last couple minutes, I just checked the weather for Friday, and it is saying it's going to be cool. It's going to be, I don't think, any higher than 60 degrees on Friday. And there are supposed to be some showers in the evening, but we should be okay weather-wise to launch Friday at 1. It's going to be on Zoom, and I sent the details out to everybody. Mr. Zwartz, one of the other physics teachers, and some people from the astronomy club should be joining us, so we should have a pretty good group. Hopefully I don't blow myself up. That would be pretty crazy if I blew myself up, but the chances of that happening are pretty slim. When you launch model rockets, you have this little control panel that you use to ignite the engine, and I believe there's like 15 or 20 feet of cord between, or 15 or 20 feet of separation between you and the rocket. So even if it blew up, there's such a small amount of propellant in there that it wouldn't really hurt you. Okay, some of the larger model rockets that will go really high up, we're talking like thousands of feet. Those have a much bigger engine, and that could potentially cause some damage, but you're way far away when you launch those. This is small stuff. So I have the Red Rider right here, and also the Alpha 3 that I'm going to be putting together tomorrow so that I can launch these on Friday. The engines that I'm using are fairly small. It's really hard when you get a rocket way up there. Like anything over like 1,000 feet is really hard to track visually. They do make devices that you can put inside of rockets. Let me see if I can find a picture. Let's see. I have all sorts of really crazy devices in here. Shoot. Let's see. Yeah, so there's something like this. This is called a micro beacon. This just makes a really high-pitched sound so you can hear the rocket. But I know there's GPS trackers and all sorts of other weird things you can put in there. The problem is a lot of that stuff requires a battery to operate. So you do need a fairly large rocket to fly that up. The rockets that I'm using are very small, so there isn't even a compartment inside of these to put anything. So these you just have to track visually. But the engines that I'm going to be using are very small. They're only going to go up a couple hundred feet, so it should be easy to track these. Another issue that you run into when you launch really high is the wind will carry the rocket. Once the parachute deploys, it'll carry it, way downfield. If you're not launching it in a really big open area, you could have it drift into trees, houses, all sorts of things. So I'm going to keep this relatively easy and simple, so we're going to be using smaller engines here. Okay, so that's going to be Friday at 1 o'clock, and it'll be on Zoom. So if you didn't get the details, please let me know. All right, the question of the day is, what is your favorite video game of all time? And that video game should be the one that made you the most excited to play. Played it all the time. You could probably play that game now, 10 years, 20, 30 years from now, and still be just blown away by that game. So my favorite video game of all time is Final Fantasy VI, which was Final Fantasy III in the United States. It was released on Super Nintendo, and you might be a little confused by the numbering, and everybody was back in the day. So in Japan, they had released, this was the 6th version of Final Fantasy, but in the United States, they had only released 2 versions on the original Nintendo. That's the old school Mario Nintendo at the time. So this one that they released on the Super Nintendo was actually the 3rd version at the time. No, wait, I got that story wrong. They only released 1 on Nintendo, and they had released another version on Super Nintendo, so that was 2. So this was the 3rd one that they released altogether. So at the time, the graphics were amazing. On the right here is a screenshot of the game. It's a role-playing game, and it's got a very large story. I mean, I think it probably takes at a minimum 12 hours to play all the way through the game, but you could easily spend more than that, 20 hours playing the game. It was a very long game. Nowadays, games can be much longer than that, but at the time, it was a very, very, very large game. Okay. One of the cool things about the game is it wasn't linear, so you could kind of once you got to a later part of the game, you could pretty much do stuff in any order you want. You didn't have to complete all the things to beat the game, so it was kind of cool. I got it for Christmas one year and played it all the time. I played it many times through, so I really enjoy this game, and it's my favorite game of all time. So some of my other favorite games, for those of you that are interested, Final Fantasy VII on PlayStation. It is a really hard call between 6 and 7, which one's my favorite, but still think 6 because it was the first that I played. 7's a really good one. It was on the PlayStation. They're remaking the game right now for PlayStation or PC or something, I don't know, but it should be pretty cool. Half-Life, that's the original Half-Life, not Half-Life 2. This was a big game when I was in high school. Red Alert 3, I still play that game all the time. It's from like 2009. It's a real-time strategy game. Alpha Centauri, it's a turn-based strategy game. Star Trek Online, it's kind of a nerdy game, but I play that every now and then. I'm a huge Star Trek fan. Master of Orion, it's a turn-based strategy game. Love the Fallout series. I've played 3, 4. Sorry, I've played 3 in New Vegas, and I'm in the process of playing 4 right now, and I already love it. And then another game that I played a lot was World of Warcraft. Like a lot back in the day when it was big. Like everybody was playing it, and it was a lot harder back then. I knew that I had a problem and needed to stop because I was playing like 8 hours a night. So yeah, I haven't played World of Warcraft in probably like 10 years. So anyway, let's move along here. All right, tomorrow we do not have a live stream. Tomorrow Fermilab is doing a talk on the Large Hadron Collider. It's going to be at 1 o'clock on Zoom. If you're interested, you do need to pre-register. I'm going to post the link again here. But let's see. Oh, I just got an email from Fermilab. It says they're going to send the email to everybody. Okay, so they're going to send the meeting information tomorrow from 11 to 12. So if you did pre-register already and haven't gotten the email, don't panic because they're holding off sending out the Zoom details until tomorrow. I'm not quite sure why, but she just sent me an email. I emailed her because I hadn't received my information. But let me post the link one more time if you're interested. You do need to sign up in advance, and the link is right here. So let me post this again. Okay, so if you click on that link, it'll bring you to a Google form, and you just fill that out with your information and your email address, and they're going to email you a link tomorrow before the event so that you have all the information. It's just going to be on Zoom. I've used this before, and I'm assuming it's going to be just like them. I'm also guessing that they're going to mute all of the participants when you come in, so just be mindful of that. And they might, I don't know exactly how it's going to work, but it should be very interesting. If you don't know what the Large Hadron Collider is, it is a particle accelerator. It's the largest in the world. So Fermilab is located in Batavia, kind of over by the St. Charles area, St. Charles High School. And this is the particle accelerator that they used to have in operation. I don't believe it's been operating for the last 10 years or so. I think like 2009, 2010 is I think when they stopped it. But it was they did a lot of really cool experiments here. It was a 3.9 mile circumference particle accelerator. And if you've ever been to the Fermilab campus, it's pretty cool. It's like a nature preserve. And the main building is kind of over here. It's a really cool looking building. If you ever have a chance to go there, I highly recommend it. But the particle accelerator hasn't been in operation. It shut down due to budget cuts, and then also the Large Hadron Collider came online. So here's a picture of the Large Hadron Collider on the inside. Okay, it looks like some massive piece of science fiction technology, and it is a marvel of modern engineering. There is a 17-mile underground tunnel with this thing, so it moves in a circle just like the one at Fermilab. But it's a much, much bigger and more powerful particle accelerator. So if you look down here in the lower right-hand corner, this is a picture of the tunnels that carries the particle accelerator track around. And they basically take little tiny atomic particles and they smash them together. And they can do some really cool things with this. If you remember, it's been a couple years, but they had they found the Higgs boson particle, which was referred to as the God particle. And a couple years ago, and that was a really big breakthrough for them. So once they get this thing up and running, like complete to capacity, they're predicting that they're going to be able to do a lot of really cool things that we couldn't figure out before. So they're going to be talking about that tomorrow at the Fermilab talk. So if you do attend, I just need you to shoot me an email and let me know something cool that you learned about it during the talk. All right, so just shoot me an email afterwards and let me know. All right, it's at 1 o'clock, and I'll be in there too. I'm super excited to hear what they have to say. And that's it. So I'm going to move on to chemistry. So today we are going to go through the optional practice for the heat of formation. And tomorrow I am not live streaming because I'm going to be in the Fermilab talk. So this is the last live stream of the week. Friday we do have a quiz over the material from Monday, Tuesday, and then the heat of formation information from today. Heat of formation material. Let me grab my sheet here. Okay, so what I'd like to do, even though nobody's really watching me, I'm still going to go through these for those of you that are going to look at it later. I'm going to go through the practice problems for the heat of formation. Okay. My daughter's birthday. She's super excited. All right. So let me pull this up on OneNote so we can take a look here. All right. So for heat of formation, we were looking at chemical reactions and we were trying to find the delta H. Okay. Remember, the delta H value is the difference between the products and the reactants. Okay. So on the curves that we were doing with our potential energy diagrams on Monday, Tuesday, there was a difference on that graph between the products and the reactants. Okay. So our equation is given to us up at the top here. So the delta H of the reaction is equal to the sum. Remember, this Greek letter right here means the sum. The sum of the delta H values for the products minus the sum of the delta H values of the reactants. Okay. So it says, given the following balanced chemical reaction, calculate the delta H. All right. So what I'm going to do is I'm going to highlight the left side, which is the reactants, and the right side, which is the products. Remember, anything that is by itself, we can cross off. So aluminum is by itself, we can cross that off, and hydrogen's by itself, so we can cross that off. Okay. Anytime you have something where it's in its standard form, the delta H value is 0. So we just cross those off. You don't need to figure those in your reaction. Okay, so delta H is going to be so we need to do the products. So we're looking on the right side. So we're looking at this Al2O3. And then up in the table, it tells us the delta H value. But we have, we only have 1 mole. So this is just going to be that value. So negative 241.8 kilojoules per mole. I'm going to leave the units off just to make it a little bit easier. All right, and then we're going to subtract the delta H values for the reactants. So for the reactants, we're looking on the left side here. And then notice there are 3 moles of water. So this is going to be minus 3 times the delta H value of water, which is negative 285.8. Okay, so let's simplify this a little bit. So this will be negative 241.8 minus a negative 857.4. Now when you have double negatives, that's the same as adding right here. So this is the same as adding these numbers. So negative 241.8 plus 857.4 gives us a delta H value of 615.6 kilojoules. Okay. Part B on here says, is the chemical reaction endothermic or exothermic? Is heat absorbed or released? Okay. We have a positive delta H value, so this is going to be exothermic. Oops, I'm sorry, endothermic. Okay, and that's because we have a positive delta H. So if you're endothermic, you're absorbing that energy. So energy is absorbed. All right, not too bad. Let's move on to number 2. Number 2 is a little bit more complicated. So we have our equation, and same thing, I'm going to separate it by products and reactants with color here, if my pen will cooperate. So on the left side, I have my reactants. On the right side, I have my products. And then I want to look and see if I have anything by itself. So H2O is not by itself, CS2 is not by itself, H2S is not by itself, and CO2 is not by itself. Okay, so I'm going to need delta H values for all of these. So delta H is going to be products minus reactants. So the products, the right side, is going to be 2, because I have 2 moles, 2 times the value for H2S, which is negative 20.0, plus CO2. CO2 is by itself, so I just need one of those, which is negative 393.5. Okay, and then I'm going to subtract the reactants. So I have 2 H2Os, so 2 times H2O, which is negative 285.8, plus the CS2, which is negative 117. Oh, kind of ran off the screen. All right, now when you do this, you can do this the way that I did it in the screencast, where you figure out the delta H values of the left side, and then you figure out the delta H values of the right side and put it into this equation. Or you can do it like I just did it right now, where I put everything in brackets. Okay, and it's important that you use brackets, because this negative right here, when I subtract it, will apply to the whole right side. So I'll show you what I mean here. So let's work out the left side. So 2 times negative 20 is negative 40. Negative 40 plus a negative 393.5 is negative 433.5. Okay. All right. So then minus, and then 2 times negative 285.8 plus a negative 117 is negative 688.6. Okay. Now, if I didn't have parentheses or brackets on the outside, I might have only applied that negative to one of the numbers, and then I would be wrong. So remember, that negative is going to distribute to the whole thing on the inside. So this negative is going to apply to this. If I'm confusing you, just do it the way that I did it in the screencast, okay? And actually, for the next one, I will do it that way. Okay, so for this one here, we have a double negative, so that's going to be just like a positive here. So negative 433.5 plus 688.6 gives us 255.1 kilojoules. Okay, same thing. The delta H value is positive, so this is going to be endothermic. Because we have a positive delta H value, and energy will be absorbed. Okay, let's move on to the next couple ones here. On the backside is a little messy because we have quite a few problems here, and then we have a table down at the bottom. We have 2 tables down at the bottom. Okay, but this is basically all of the information for all of these problems, whereas in the ones up here, it gave us the necessary information for just the one problem. Okay. So I'm going to do the first one here a little different. I'm going to do this the way we did it in the screencast. Okay. So either way is fine. If you're really good with math and you can keep everything straight, do it the way I did it for the second example. But I'm going to do this next example, and I'm going to break it into parts. Okay, so our delta H of the reaction is equal to the sum of the delta H values for the products minus the sum of the delta H values of the reactants. Okay, so what I'm going to do first is I'm going to find the delta H values I'm going to find the sum of the delta H values of the products, the right side. So the right side is CaF2. So I'm going to go down to the bottom. CaF2 is negative 1215, and I only have 1 mole, so negative 1215 plus 2 times, because there's 2 moles here, 2 times the delta H value of NaCl. NaCl is negative 411.1. Okay, so let me do this. I don't have this broken down on my notes here. Pull my calculator. Ah! Great, now I broke it. I broke one note. Calculator doesn't want to cooperate. Okay, so 1215 negative plus 2 times, oops, 2. Let's do this a different way. Not a big fan of the calculator on here. Give me just a second. What did I do with my calculator? Really disappointed. I left my calculator at school. Here it is. I left my calculator at school, so I have to use this emulator here. Okay, so 1215, so negative 1215 plus 2 times negative 411.1 gives us negative 2037.2. Okay, and then let's do the reactants. So the sum of the delta H values of the reactants, so that is the left side here. Okay, so we have 2 moles, so 2 times NaF, sodium fluoride, is negative 575.5 plus calcium chloride, CaCl2, is, we only have 1 mole, so that's just going to be negative 795. Okay, so 2 times negative 575.5 plus negative 795 is negative 1946. Okay, so then it's just going to be the yellow minus the green. So let me get rid of this for a second. Running out of space. So negative 2037.2 minus a negative 1946. And remember, double negative means addition. So when I do this on my calculator, negative 2037.2 plus 1946 gives me a value of negative 91.2. kilojoules. All right, I think I only have enough time to finish this one up here. So the delta H value is negative, so that means that this is going to be exothermic. And remember, if things are exothermic, that means that energy is going to be released. Okay, so all the other problems on this page, B through E, the same thing. You're just going to look up the values in the table. So if you're really good at math and you want to kind of do it as one continuous math problem, you can. Just be careful and use parentheses. If you're not good at math and you want to do it in steps, do it this way. Okay, either way will get you the same answer. It might be a little bit more work to do it like this, but it's a little bit easy, or you're less likely, I think, you're less likely to make a sign error if you do it this way. Okay, but you know, if you feel comfortable doing it this way, do it this way. You do you. All right. Well, it was fantastic working with nobody today, but hopefully somebody will come back later and watch the stream, so I feel better about taking the time to do this. All right. Tomorrow we have our Fermilab talk, so I hope to see you guys on at 1 o'clock. And then Friday we have our model rocket launch at 1 o'clock. All right, so should be an exciting rest of the week. I hope to see you guys tomorrow and Friday if you can make it. That's it. So